Good morning. Thank you very much for coming. As we had said in our call for this session, what we're going to be talking about is our method to deal with the madness of performance. I believe that we have when we have made benchmarks, we have stumbled upon surprising results in terms of something that didn't give us the performance that we hoped we had coded into the software, or it gave us more performance. Fortunately, this is one of those happy cases in which we did effort that we didn't think was going to give us really great performance, but it ended up giving us great performance. We are Eduardo Madrid, yours truly, Jamie Pond that presented yesterday. I hope that if you're interested in this subject, you can visit his presentation when the video comes out. And our collaborator, Scott Bruce, that could not make it to the United Kingdom. What is the objective of what we're going to be sharing today? Again, talking about methods that get us close to getting good performance from the efforts that we put into the software making. And the outline of what we're going to be doing is we're going to start from some benchmarks that measured the effectiveness of our code. And we compared those efforts to the results from the library GLIBC. As you know, GLIBC is probably one of the most important libraries in all of software engineering because to a degree, I love to say that it runs the world because it is underneath everything, including Linux, Mac OS, and many other platforms. So it is like the implementation of the C standard library. And well, we are comparing our efforts against glibc. We got surprises and lessons. We're gonna attempt to learn from these things. And after somewhat superficially studying what might be the lessons that we can get from this comparison, we're going to attempt to dive much deeper into what were the techniques that gave us good performance. And then we're going to generalize even further to the meta stage of if we do this frequently, then what is it that we are really succeeding on? Okay. So the motivation for having done this work began with a very simple objective, which was we have a sophisticated library, and that forces people to think in a different way because we ask people to do parallelism for something that for applications that in general people have not applied parallelism for. So our users will have to think in a slightly different way. And to illustrate how to think in this different way, I decided myself to prepare some demos that say, hey, you understand, for example, the standard library for the C language string functions. Let's see how we are going to implement them using the parallelism that our library unlocks. At the same time, everything that we do in the SU libraries, we want that there is a very direct map to reality, that we can see how what we make in the SU libraries reflect in reality. So I wanted a comparison that in principle was a good comparison against something very real. I believe that the string operations are very good for this comparison because when they were designed, they didn't have parallelism in mind. But recently, because of different approaches and the fact that parallelism is ever more important, those string operations have been implemented with parallel operations in mind. So this is not designed for parallelism, but not hostile to parallelism either. So it's like a good type of application. They are well known, and in principle, GLIBC must have implemented them well enough because it is a very serious project that runs the world, right? So this is the list of the benchmarks results that we get from the command line. If we have the opportunity later on and the interest, I can run for you an online demo of generating these results. And in the textual format, it's not so easy to understand what's going on. But we have the graphs to show for it, okay? And we have done these measurements in our respective laptops of an Intel and an ARM laptop. And you see that where it says GLIBC, the bars are taller than the equivalent in the either SU natural and SU with platform intrinsics. So you can see that we have basically comprehensively had, in the case of the function of a string length, a much better performance than glibc. And I hope that that motivates us to really dig deeper into the implementations of these functions. And then we also measured the conversion of alphanumeric characters to integers, the well-known functions of a to I and a to long. And again, we have pretty much the same results, other than in the particular case of as alphanumeric to long, we are getting that in the ARM platform, the implementation is better than ours, and we are investigating why. And this is a work that has been in progress since more or less January of this year. So we're still seeing new insights and incorporating them into the code. Jamie posed to you an interesting tidbit that we're going to revisit very soon in this presentation. That is an indication that this is very much a live project that we are improving as we go. So the really important part of this is that our function to convert, so string length had overall better performance, but now in particular, our function to convert strings to integers is over 3 times faster than the standard library implemented by glibc of A to I. And our implementation doesn't use any hardware SIMD, and neither the glibc implementation uses hardware SIMD. So this is like an apple to apples comparison. So we get 3 times the performance that they get. So before we dive into the details of these implementations, let us recap what is it that we're doing here, right? What are the results that I am communicating to motivate the rest of the presentation for you guys? We have made a very deliberate set of benchmarks that you can audit and verify for yourselves, in which everything is random, so that there are no magical numbers that can interfere by mistake or coincidence the results. We use techniques like, for example, when we have large counts, we made it so that those large counts are prime numbers, so that if the benchmark is repeating, the processor have fewer chances of learning that pattern, because the prime numbers will make it so that when it starts the second go at the same collection, it doesn't follow from the previous iteration. We didn't attempt to have any adversarial bias. Like we're not making benchmarks to make one look better than the other. Just the benchmarks we thought were the most sensible for the thing that we're measuring. And we have an extra source of confidence that the benchmarks are fairly solid, because they catch 2 style benchmarks that are structurally very different to the benchmarks in the style of Google benchmark, show basically the same results. Okay, so we're going to see that in a moment that our implementation of a string length was made natural in another flavor that takes advantage of a small improvement. And we are also implementing it in for ARM SIMD, that's ARM Neon, and for x86 AVX2. And well, our surprise was that we got much better results, right? So our implementation for string length beat glibc always. And if you see we're past that, but the performance of our portable implementation in ARM is very close to the performance of the platform-specific ARM Neon implementation in the M1 platform. So let's see for a moment what is this natural implementation of a string length. I have the code here for you. We're going to go to the actual GitHub repository in a moment. But for the purposes of the presentation, I just wanted to introduce to you the code as it is. And let's start by highlighting some of the things that are happening there, right? So that first line is an alias that says our implementation of a string length that I call the natural flavor, which is not the best, but is the easiest to explain and to introduce, uses our SWAR container within the SWAR library. And what we're saying is that number 8 means that we're going to have 8 elements in a 64-bit integer, 8 elements of 8 bits each, basically 8 bytes, 8 characters. And what we do is something very important, which is to start by making sure that we are doing alignment, that we are loading bytes in an aligned way. And the reason being is very simple. When you have an arbitrary pointer, the bytes that that pointer are allowed to potentially cross a page boundary, but we don't know if our string is going to cross the page boundary. So we don't know if it is legitimate to read all 8 bytes from the beginning of our string. What we can say is, well, at least we can read from our input the bytes that belong to the current page, to the page where the input begins. And for that, we do an aligned load. And that's a complication that happens when you're using parallelism. Everybody that does parallelism with anything has to have that taken into account, because otherwise you're going to have problems that appear very rarely in the computer, but are severe problems when they happen and difficult to track. And this block align load will return you what is the base pointer, the pointer aligned to the natural boundary. It's going to tell you what was the misalignment of the source pointer, and it's going to load into the initial bytes the bytes that it could read in an aligned way. So right after we have read that first part of the input, we need to make an adjustment because, like I said, in our block of bytes, we will have at the beginning bytes that do not belong to our input. In the general case, we cannot guarantee that all of the bytes that we got belong to the input. So we need to do something for the bytes that are not in the input in particular. We fill them with ones because the ones are going to be something that will not interfere with the rest of the string length. And then we enter into the actual loop. We have basically established the invariant for the loop. And we use the primitive equals in the library that is going to tell us what lanes, what bytes in the collection of bytes are going to be equal to 0. We're just comparing against zeros, something I hope that you can see is rather natural. And this is going to give us something that is a collection of lanes that have booleans in them. But that collection of lanes that have booleans in them, it has a natural conversion to a single boolean, which is if any of them is true, then the whole thing is true. So if there is a null, we use the primitive that gives us the index of the first null from the least significant to the most significant. This is in little endian, the least significant. And with that index, we know how far from the base, and we can subtract the original pointer that we had, and that's the answer for a string length. I think that I took even longer than Jamie to explain this than him yesterday, but that's the essence of it. And then we add to the base and copy the bytes to try again to find the null in the next block of input. Now, the next block of input is easier because we don't have any concern about attempting to load invalid memory. So it is much easier. So I believe that this is not that harder compared to the straightforward serial implementation of a string length. And we don't have to do much effort to write this, as you can see. Of course, provided that you have a library that at least that gives you the primitives to express these parallel algorithms. So we can see right away that this is live in the GitHub repository under su benchmark c string functions, c string.cpp. I'm actually pointing here to the proper implementation, but the natural is somewhere close. So we're going to keep this link for a moment and continue. Okay. So in the case of our source code, we can see that we have, this is what I was showing for you a moment ago in the presentation, the natural formulation that relies on the primitive of equals. And this implementation is slightly more advanced, and it is very well documented because at the time in which we put this into the master branch, our understanding was what we put here, but like Jamie showed you yesterday, we have moved past that, and we have in the pipeline just about to push to production to master the new thing that we are working on, which we are calling pseudo Boolean swarts, but I'm not going to bother you with going in that digression at the moment. It's just, again, I am trying to emphasize that this is a work that is improving quite fast. So we have here the implementation for using the Mycroft trick, the natural implementation. We have here the implementation using AVX2. And I just want you to make the observation that despite this formulation using AVX2 intrinsics, the general outline of what is going on is identical to what we had in the natural implementation, which is, well, if the comparisons give us that there is a null, then we're going to do the arithmetic to identify where it is and do the computation to return the value. And if not, then we're going to progress by reading the next block of data and making the mask of the results of the comparison. So whether you put this here or put this here is really not important. Structurally, the loops are the same. And furthermore, if we go and see a string length in Neon assembler, it's telling me that that it is not charging. Oh, now it is charging. Good. The Neon only has a very important complication, which, by the way, is the reason why I think that the Neon is not very much advantageous, because at each step you had to do this. And the reason why I think that you had to do this is because I saw it that the assembler of Neon made by the people of GLIBC do this technique. But again, you see it looks the same thing again. Like if we're breaking the loop invariant, we do the computation of where the null was and get out. And if not, we load the next block and do the comparison, right? So what we have seen is that our implementations have a lot of commonality to it. We load a block, keeping alignment considerations. We do parallel processing to detect a null. And when the loop invariant is broken, we determine where it is and we are out, okay? So there isn't much more complication to that, right? And as a matter of fact, we considered expressing all of the flavors of a string length, including the SIMD using Harvard SIMD, has varieties of a simple template. But I thought that perhaps that was going to be confusing for the presentation, because we can see from the code that it has a lot of commonality, and you can trust me that we can put it into a single template. But if I put it into a single template, then we'll have to use type traits to investigate what is the way of doing the comparison and so on, and that's probably going to be confusing. But if you think that I am speaking idly, just wait a couple of months and you'll see in the repository that all of these functions are implemented consistently using the same the same code style. They are going to be just arguments to a template. Yeah, so in recap, they all work with a block of bytes in parallel. This is harder to write, but not much. You need to work with potentially misaligned input pointers, and to guarantee that you don't consume invalid memory, you read aligned, and you fill bytes. You complete your block of bytes with things that are not going to interfere with your computation. And I hope that you noticed that there was only one conditional branching, the detection of the loop invariant being broken, and that's the minimum that you can have in something that has a loop, right? That the loop invariant was broken. So this is minimal and optimal in that regard. Now, the question is, do you think that this is a natural implementation? We've observed an improvement. We first observed a better way to do this in GLIBC, which is based on the fact that in the code that I showed to you, we, at every comparison step, check for all of the nulls in the block of bytes, but we don't need to check for all of the nulls. We only want the first null. And therefore, this is the opportunity to do something slightly better. And it turns out that from this insight, we managed to identify that this has been discussed in The Art of Computer Programming by Donald Knuth, and our coworker Scott Bruce said, you know, this is actually a family of techniques in which we don't care about all of the Boolean results, just the first in the little endian encoding, and we gave it the name of pseudo-Boolean swarts. So that's why if you Google for pseudo-Boolean swarts, you're not going to find anything, because this is something that we are giving it a name. And as far as I know, nobody else has given it a name. But it is a new family of techniques that we are developing and taking advantage of. And just for your peace of mind, this is because this is code that is meant to work as a demo. This is properly documented in the sources, okay? This is an example of how I documented it myself. I am crediting it to Alan Mycroft. You can go to the actual page where this is described and so on, and I take and I try to help by explaining the essence so that you can just do it on the fly. I hope that that's going to be helpful for the people interested in using the library. As we said at C++ Online, we consider this library production strength. We do use it in production. It is just that some people might be confused because it is changing so quickly. It is improving so quickly that it doesn't look to be production ready. But no, all of the improvements that we're putting in, we consider that production ready. Okay. So this is the essence of the technique. However, because I see that many in the audience also went to Jamie Pond's presentation yesterday, and you have the video available if you're seeing it this on the internet. I don't think it is a good service to anybody for me to repeat his explanation, so I am going to skip. And now we are attempting to dive deeper into the lessons that we got, right? And let's start by the third point, something that is a meditation from Scott Bruce. Our SWAR library is organically transitioning from working with integers in parallel, using a normal integer has the base type for all of the operations. It's transitioning into other dimensions that were not the originally intended. In particular, when we're using the software CMD capabilities of the library, what we have is freedom. For example, in the ARM platform, you don't have the operation of parallel extraction that I consider to be a very important operation. The parallel extraction is the name that Intel gives it to it. We can also call it compression. And the similar operation of expansion, they are not available in the ARM platform. But we have implemented it in software in a lane-wise way. So you don't only have the operation of compression and expansion for integers, you have it in a lane-wise way in the case of the SWAR library. The same thing happens with the population counts. I don't know of any CMD platform that gives you the population counts on a lane-wise way, like let's say an AVX vector that has four 64-bit integers. I don't think that there is an operation that's going to give you the population count of each of the individual lanes in each lane. We have that in the library. Or more precisely, we can synthesize that operation using the same technique that we do for normal integers, but for CMD registers. And if we want a top performance when the hardware is available, then we can use the hardware CMD. We can do mixes between hardware CMD and software CMD. We can, hopefully, we have not proven it to work yet, but we're working toward that, of having the same techniques, leveraging the specific conditions of CUDA execution or Fusion execution, basically GPU programming. And this might be very interesting for people that are doing artificial intelligence, but we're getting there at our own time. And in general, we can say that we're rendering the name of the initial name of the library, which is SWAR, a little bit outdated because it is doing so much more than what the name implies. Okay. Now I showed you the code that we implemented, right? But the code that we implemented doesn't seem to be crazy. Now I had to deliver to you on the promise that something absolutely maddening happening that's completely crazy, and our simple code somehow managed to beat it. So let's see, what is that surprisingly complicated code that I'm telling you about? This is the portable implementation of a string length made by the people in the GLIBC project. You can see that this is the official repository. And this is what used to be the portable implementation. They changed it relatively recent, but the new implementation is hard to explain, so I'm going to just use the previous to latest. And this is the way that it does it, okay? So I'm just gonna go through, just the attitude conveyed by the use of the identifiers, like for example, long word, high magic, and low magic. They don't make any attempt to explain what the meaning of long word versus low magic is attempting to mean. They have the expressions like the complement of the long word in conjunction with the high magic, something, and so on. So you can spend your time attempting to understand this, and you will see that it's not very natural. And when they decide that they need to get out of the loop because they have found a null, which is in this particular if they find that they have broken the invariant, then they begin a very painful, from the perspective of performance, if then else cascading of, well, if the thing was in the 0th position, then I'm gonna return this. And if it was in the 1st position, then return this, and so on, right? So 7 cases in a cascade of if then else's. This is something like doesn't look to be good. This is I should have used this slide, but the point that I'm making, I already. One characteristic is that I believe that advanced and critical techniques deserve good explanations, and this code doesn't have them apparently. I think that style of coding is very rigid and intimidating. Like people will try to not have to deal with it because they know that it's going to be a headache for them. I don't believe that our code has that problem. That you can naturally see what's going on, and therefore you feel amenable. Oh yeah, I think I'm just going to make this change because I know that it's going to be beneficial. And the cascading of if then else's is a very important performance pitfall as time goes on, because the branch prediction in modern architectures are ever more important. So the more amenable, the more friendly you are to the branch predictors in your processors, you're going to get better performance. If you use techniques that are inherently wasteful of branch predictor resources, you're going to just unnecessarily damage the performance of your code. Okay, now this will be a good time to just go to sleep if you feel sleepy, because this is nearly incomprehensible. It really took me effort to understand what this assembler is doing. And mind you, this is for something very easy to understand, the same string length that we have been talking about, right? And so they go about and go about and go about more and more things, and considerations like they had to make sure that they're not crossing page boundaries in an explicit way. And let me see if I can get my bearings, because it is not so easy to even get your bearings on this code. Yeah, but like I believe that this is the main loop of this handcrafted assembler, okay? And you can appreciate, hopefully without too much trouble. Sorry, is there a question? It's without too much trouble, that what they're doing is to unroll the loop forwise. Like they are having 4 iterations here. But mind you, each of these iterations refers to 32 bytes, okay? So they are doing work on 2 cache lines at a time per iteration. And I don't think that degree of extreme aggressiveness in loop unrolling is justified. And then they have even more complications, because they say, for example, save some code size by microfusing the the minimum operation with an unaligned load with the load. So they are loop unrolling forwise, but at the same time, they are putting an altogether different code path to fuse the load with the minimum operation, which is a different comparison to what they're using in the other side for the purposes of reducing binary size. I don't think, I believe that this is a contradiction in objectives. And I honestly don't understand why they keep RDI misaligned in this particular code. So let's go back to the sanity of our insanity, so that we go to the insanity of Neon. And again, what we see here is that the code for Neon does loading 16 bytes here, and without any branching. No, actually, with branching, but within the parameters of the label loop and loop end, you see that they are loop unrolling 2 iterations, and it begs the question why it is advantageous in Intel to loop unroll to 128 bytes, but here it is advantageous to unroll to only 32 bytes. So I don't think that that makes sense. Be it as it may, that's the way that the assembler was generated, right? There are a few properties that these two handcrafted assembler code have in them, within them. They are handcrafted assembler, but they are nothing like each other. And what I told you of fusing the BP minimum on a line load, and then there are suspicious inefficiencies like keeping these things on a line. So it beats me why they want to do on a line reads, especially knowing the problem of crossing the page boundaries that I told you before. Well, we can be critical about this work, but at the same time, I'm very happy to have studied it because I didn't know anything about how to program these things for ARM Neon. And I got this magical incantation from the ARM Neon sources, and I got to understand what that does. And now I'm able to do all sorts of masking in Neon because I can repurpose this technique for whatever objective I might have. And sure, if you want to understand what that thing does, I invite you to attempt to understand my comments for the expression of these into intrinsics. So I just invite you to see that we never felt any need to use assembler in our source code. We mostly use C++ for everything, and we just peel up the hood a little bit, put in an intrinsic via C++ wrappers, and we don't lose performance because I just show you that our stuff beats comprehensively the handcrafted assembler, right? So another property that the effort in GLIBC exhibits is that they put a lot of effort into it, right? And the real question for you guys is how would you improve this code? If imagine that for some reason you are in your job environment and your work environment and the need to improve that code for whatever reason appears, would you feel a little bit of despair of having to understand that assembler and scratching your head and how am I going to do it? I don't think that our users have that experience with the library that we have been working on, right? So before we go to see the sources, our sources in the Compiler Explorer, this would be a good opportunity for you to ask any question if you might have it. No questions so far? Okay. For the people watching online, they don't look to be asleep. So. Okay, I'm gonna sit for a moment. I don't know. Christopher, is there a function that you want to see in the assembler? Okay, let me propose perhaps the natural implementation of a string length. So we had to enable library functions and okay, so let's maximize this and let's make it larger for everybody to understand. Now, if I didn't have, so This is the entirety of the assembler for a string length, consuming 8 bytes at a time. I ask you to notice that this already is smaller than the assembler that the GLIBC people made for it, substantially shorter. And we can see, if you study this in a little of detail, that this is the main loop. This is all that is required to consume 8 bytes of input from the purposes of detecting where the null is. And well, the performance is there, right? So we can also see why don't I have AVX? Because I'm searching in the wrong place. Yeah, for a moment I got scared that I did the wrong Compiler Explorer link, but no, here it is. And hello, this is the entirety of our AVX2 implementation. This is what the assembler, this is what the C++ code becomes when translated to the assembler. And there is only one main loop, and it is composed of just 5 assembler instructions. Okay. I believe that this is enough because on your own you can pick this link. It is not very easy to see on live, but when you have the slide, you can click on it and play yourself with finding the assembler or making the changes that you might want. And I ask you, do you think that this is an elegant way of writing these operations? So now we're going to shift gears into something far more complicated, which is to compare the GLIBC implementations of ASCII to integer to our implementation. You can go and of course see the sources for A2I online and try to understand them yourselves. They are not particularly easy because everything uses the string to D and string to L, the family of functions of string to L that take into account locales and so on. But yeah, you can plow your way through it. I don't think it is a good service of the audience for me to explain it right now, so I'm going to skip on that. But it is very important to understand that the A2I is a much more complicated function because you have to take into account the leading spaces before you begin to parse numbers, the fact that there is an optional sign in there, it can be the plus or the minus sign, then you can start with a number of insignificant zeros that can be arbitrarily long, and then the numbers that you're going to be converting to binary from base 10 to base 2, and then the non-digit character that terminates the sequence of numbers, right? I think that people did not anticipate that the SWAR techniques were going to be very advantageous, because otherwise everybody and their dog would have done it already. But I thought that it might. I just wanted to see, well, if it doesn't give me the best, has good performance, then I would like to see why, right? By the way, this presentation has a lot of selection bias to it. Because of course, if I would have done benchmarks that working less, I got worse performance, then there wouldn't have been anything novel to tell to anybody, right? So to a degree, this is just the product of mere luck. But notwithstanding that, there might be some deeper lessons that we can learn from. And I think that one of those lessons is that what the people in GLIBC did of putting a lot of effort into handcrafting the assembler and so on ended up actually being counterproductive, not even not beneficial, but contrary to beneficial. And that is not luck. then the core, so those are the extra complications in the conversion. But now we also had to focus on the conversion itself of a lot of conversion of groups of bytes into numbers, right? And that has its own complication because from the perspective of a machine that is in little endian, the most significant number is the first to appear in the alphanumeric string, but it's going to be the one that is in the memory position furthest from the beginning in the result. So we, in a way, we had to invert the endianness of the input. We have to detect the end of the input along with the conversion. And we need to measure the performance of using 128 bits by combining two 68 bits, like the infamous data type of uint 128T. So one thing that I'm just gonna go to the source code for the purposes of showing this to you. So there is someone that has been writing about performance for a long time and has a lot of insights to share with the community. The name is Professor Daniel Demois from the University of Quebec, I think. And the core of the conversion of characters to integers is his best method to convert characters to integers is this function that I am highlighting for you. So we can forget momentarily about receiving characters because we can transform those characters into numbers by subtracting the collection of characters equivalent to the character 0, right? So if you subtract 0 from a character, then you just have its value number. And what he does is to have 1 on the low side and 1 in the, 10 or 100 or 1,000 in the upper side. So again, I don't think it is a good service to the audience for me to explain in detail how to do the conversion, but you can go to the blog of Professor Lemire to understand what he does, and you can try to understand the code. But we can also use our own implementation that it is also explained that does the same thing, exactly the same mechanism, but using our SWAR library. And what is happening there? That we follow. Sorry that I keep double clicking by mistake. That was not a double click. We have things like this. We're going to multiply by a constant that is a 10 in the upper byte and 1 in the lower byte. And then we're going to multiply by 100 in the upper 2 bytes. Sorry, 100 in the upper 2 bytes and 1 in the lower 2 bytes. Then it will be 10,000 on the upper 4 bytes and 1 in the lower 4 bytes, and so on. And the key is that we're using the double precision modifier for the SWAT library. And that is what allows us to have to skip this non-trivial shifting that is happening in the shifting and masking that is happening in Lemire's code. So I believe that this is an improvement, that the use of the SWAT library makes it easier to focus on what you're doing. And that is what allowed us to upscale that code that uses 64 bits to use the pseudo 128 bits that the platforms offer you by combining to 64 bits via the compiler. So these operations are going to be more expensive, of course, but that's not the issue. The issue is that they are available and we can use them. And so this is a generalization of what, I keep doing it, a generalization of what you just saw before. And this is the front to convert the characters. So what is it that we're doing here? We are, what I'm attempting to convey to you how this library helps you by relieving you of taking care of minutia and details that are very error prone. And then therefore it allows you to combine things in a more efficient way, efficient in terms of effort, and that effort preserving benefits of the library translate very frequently into better performance, because you can be more attentive, you can understand better what's going on and identify the mechanisms that are going to get you the result better. Okay, this is the simple implementation of spaces using GLIBC. You just call the standard function isSpace. And this is my implementation using the SWAR techniques. This is a template, but it is meant to receive a SWAR. I put in the comment what I expect and what I'm trying to do and so on. But the essence of what we're doing is, well, we use the SWARs equals to detect the bytes that are exactly equal to the character of a space. Then we use the constant is greater equal to the carriage return to detect those that are below the carriage return, below equal to the carriage return. Then the below equal to the character prior to the tab. And this is what equals, and the range, if it is an equals or is in the proper range, then it is part of the output. And if not, then it's not part of the output. And that's it, right? So this function, leading spaces count aligned, assumes that the input is aligned. Actually, it should be called leading spaces block. And now it is when you get a pointer. And when you get a pointer, you need to do the same block align load that we have seen before. And we end up invoking leading spaces count. And then if we didn't increase the count by 8, that means that there was a character that was not on a space, and we take that into account. And if not, then we could keep on going. So this is another example of how to do this. So I put all those things together, and of course, I got so much better performance. Maybe we can go back to the slide with the benchmark. So is there someone who cannot distinguish between red and blue in the audience? Nobody is raising the hand. We can focus, just because my computer is x86 in the blue lines, and you can see that the GLIBC, which is the blue lines, are always taller than the comparative for the SU library. Like, for example, in the case of GLIBC for Intel, this thing requires 40,000 nanoseconds, but in SU it required 20,000 nanoseconds, so a factor of 2 improvement. In the ARM platform, the difference was not as pronounced, but it was pronounced nonetheless. And we see here my attempts to use 128 bits that have been partially successful, only partially successful. I had to dive deeper into how to truly get all of the performance needed. And I am not ashamed of showing you that the A2 long implementations continue to be much better than GLIBCs, but substantially worse than the ones that don't use the ones for A2 integer as opposed to A2 long. Uh, okay, so now now that we have seen many examples of things that in the Zoo library perform better than much larger amounts of effort done by the people that implemented these functions in glibc, and by the way, that's what the whole world uses, maybe we can ask what are the things that we're seeing that are performing well. So the most important part of it all is that you had to work in a way that is friendly to the caches. Space and time localities must be preserved. You have to have a really good understanding of the concept of a cache line, because every time that you're doing a memory access, you're not accessing only 1 byte or 8 bytes or whatever. You are consuming an entire cache line, and if you're writing, then you're probably reading, updating, and writing back. You also have to be aware that the cache entries are, the caches, of course, are much smaller than the main memory. So there has got to be a mapping for the things that you actually have in the cache versus the things in memory. And that mapping can lead to conflicts of two different positions in memory wanting to go to the same entry in the cache. And that's the problem of fault sharing. Again, I am not in the position to explain to you all of these things in this presentation, but I'm just putting it together for you so that you have a comprehensive idea of the things that you have to take into account. There is the importance of space efficiency in terms of the data is very clear, right? But for people, it is less clear the importance of that object code ought to be very efficient itself, because otherwise your caches for instructions, your instruction caches are going to be inefficient and therefore less effective. There is a problem. I do love Clang. That is my favorite compiler. You have seen me advocating for Clang many times before, but it is absolutely crazy with regards to unrolling. It is far too aggressive, and the behavior is impossible to control. The loop unrolling is decided so early in the chain of optimizations that by the time that an optimization like a compile option like -f no loop unroll is taken into account, is far too late. The unrolling has already happened. So it is a situation in which Clang makes it a leave it or take it or leave it with regards to performance. Sometimes to get better performance, not size, to get better performance of my code, I compile with a -z of Zebra. That is a very aggressive code reduction set of optimizations, or maybe even -s of SAM, because optimizing for size in Clang ends up being superior to optimizing for performance for the purposes of better performance, because of how aggressive it is at loop unrolling. Another thing that can kill you in terms of the results that you get for the efforts that you put into doing performant code is to have naive benchmarks, because naive benchmarks are going to be profoundly misleading and are going to take you away from the end result. My hunch of what happened with glibc is that they had benchmarks that were not representative of what they wanted to measure, and that misled them into going into profoundly counterproductive avenues. But that's my speculation. The other part that you had to be very aware is to understand out of order and speculative execution and branch prediction in the processors. This is one of the keys. Like in modern architectures on today and for the foreseeable future, doing things like loop unrolling are bound to be profoundly counterproductive. because it is extra effort that you're going to put into it. And the performance is not going to be there. And you can read the slides, but I'm just going to give you the gist of it in the interest of time. The real problem is that loop unrolling is over-specifying. The processor itself is going to be able to continue to issue and dispatch instructions to all of the available execution units, because as long as it has execution resources to execute instructions, the dispatcher, the decoder is going to dispatch instructions to those execution units, okay? The only way in which you're going to disrupt that process that the processors are going to be doing, as a matter of course, is if you tell it to do something different, because that's what you think that the processors are able to do. So don't do that. Don't over-specify. In our case, you saw that we made absolutely no attempt to loop unroll, and we blindly, blissfully rely on the processors being able to both execute out of order and speculatively, for the purposes of having several iterations of the main loop at the same time in flight, being executed depending on the availability of resources, of course. And well, that has got to be the one reason for why our code is performed better than the code of GLIBC. So again, the lesson is, let the processor do its job, that the coding units do, because it is extraordinarily hard to anticipate what is the execution profile that your execution platform is going to give for you, even in the best of circumstances. And if you think that you can get it right, then probably your software is going to be running alongside some other software that also has demands on execution resources, and what you optimized ends up being a pessimization in the presence of competing demands for execution resources. So in general, just don't do that. Just let the processor figure out how to organize things for maximum delivery of execution. Another thing that we need to do is something that technically is called converting control dependencies into data dependencies. Of course, that this is easier said than done, so I got an example for you, which is the two's complement saturating addition that Scott Bruce made for us. And what this does is invokes the full addition, invokes the full addition, and the full addition has an output, which is the carries for each lane. And what he does with the carries for each lane is he converts the carries, which are the most significant bit on each lane, if they are there, converts the most significant bit to the entirety of the lane, and apply bitwise OR to the result. So this means all of the lanes that had a carry become all ones in the output. You see the effect of unsigned saturation. And there was no explicit if then else's in this thing. This is happening for all of the lanes of the input at once. And all of these primitives that we're working on, you see here that they are SWAR. The base type might not be integers. The base type might be themselves SIMD data types for the hardware SIMD, like AVX or Neon data types. Furthermore, you can say, well, but you have a saturated addition in the SIMD platforms. Yeah, but what if your element size is 7 bits, for example, not a power of 2? Well, this library will let you have all of those conveniences with some performance cost, of course, but we'll let you have it. So this is an example of how to transform what naturally are control dependencies into data dependencies. There are many more things. I'm just going to go over very quickly in the minutes that we have remaining in the presentation over more elements of the recommendations that we follow in the SU libraries for the purpose of getting performance. So there's a problem with micro-benchmarking that it resembles quantum physics in an important aspect, which is the measurement of performance disrupts the performance of what you're measuring itself. Okay, so it's like a micro-benchmarking is not very reliable. The measurement disturbs the experiment itself. You can go and check how noisy benchmarking is by checking the presentation by Emery Berger, Performance Matters, both at the Strange Loop and other places, because he explained this real well. Christer Walfridsson wrote in this blog post more about how brittle the optimizations and the performance measurement considerations are. So one thing that I see happening all over the industry is that people are applying benchmark results blindly, as if a benchmark result would be the ultimate thing to say about a practical consideration. And that is the wrong way to go about it, okay? You first had to have a model that you use the benchmark to test or disprove of what is the relation between what you're doing and the performance. If you do it blindly, what you're doing is to incorporate in your production code accidents from the way in which you did the benchmarking, not real knowledge of what performs well. So another recommendation that we have for you is don't do that. Put in your code real knowledge as opposed to hunches or things that have not been proven thoroughly or systematically. And the final part of the presentation is very quickly something that seems to be impossible, which is how are we going to bottle knowledge about the knowledge that we have about how to get good performance so that our users open that bottle and consume it and enjoy the performance knowledge that we have, right? It seems to be impossible, but I think that there is one key that if you succeed at this, then you're gonna be really helping your users. Because for me, it is not enough that the libraries that my team writes have very good performance, like they implement things in ways that are better than anybody else's. That's, of course, very desirable. But as much as possible, I want to go further, which is by using our library, our users are going to get more performance than they would have gotten otherwise. Because like our library puts them in the right direction toward things that really work. And to be successful at that, you can express the success into bottling performance has been extremely successful at composability. If your library is extremely successful at composability, then you have a prayer of hope of helping your users rely on your infrastructure more and more and more, and therefore there's going to be some synergy to it. Synergy is what we're looking for. And this has to do with the foundational principle of the SU libraries that I have called the epistemological doctrine of software engineering. Epistemological means a theory of knowledge. So it is how to get knowledge, how to express knowledge in source code, how to deliver knowledge for a user that's going to consume a library. The reason why knowledge is at the center of all of our efforts is because knowledge is one of those few things that compose exponentially. And the reason that knowledge composes exponentially is because it empowers. It gives you more powers. Once you have attained a new level, superior level of understanding things, that simplifies to tackle complications on the periphery of what you understand. And once you understand also the periphery of what you understood first, then you are expanding and becoming more competent and becoming better at everything, basically. Then the recommendation would be to engineer software as expressing knowledge in source code. And this is easier said than done, of course. And one of the keys of composability is the single responsibility principle. But the single responsibility principle is a goal. It is not a method to achieve it. So the rest of the slides that I have in the presentation, you can read them at your leisure and see if you agree with our recommendations or not. We are very interested in knowing the conclusions that you might get from them. But the essence of a fallacy that I see happens very often is that people prematurely commit to ideas that they don't have a really solid understanding of. There is a lot of pressure to deliver in time, therefore to take shortcuts. And one of those shortcuts is your understanding of things. So that's perfectly fine. You can deliver code to accomplish something however you can, as quickly you can. The real problem is when you commit to bad choices, to software that doesn't express knowledge, but that haphazard process of software development. And the essence of being premature is that it happens before you know. Premature optimization is a problem as bad as premature commitment. And these are comments on how we do things. Basically, we have a very strange method of how to do software engineering. Like, for example, we absolutely reject the technique of copy and paste. In general, from an outside perspective, it might be said, perhaps, I'm willing to accept that accusation, that we're meeting the madness of performance, because we have seen that we put a lot of effort into performance and we get less performance. So that's maddening, and we meet the madness of performance with our own madness, because we do things that are apparently crazy, but it is so fun. And that is the end of my presentation. Thank you very much. I think I have a couple of minutes to. Thank you. Thank you very much.